All right, welcome everyone to the very first deep dive. We're so excited to have you here.
Yes, welcome.
We're ready to just, jump into these materials you've shared
Yeah, really unpack them.
and uncover some really fascinating insights.
Absolutely. Should be fun.
So today, we're going to be diving into the world of electrical engineering.
The fundamentals.
Yeah, the fundamentals, as presented in your textbook excerpts.
Think of this as your, personal guided tour through these chapters,
Exactly, your shortcut.
Yeah, your shortcut to understanding, the core ideas.
And why they matter,
Yes.
especially in our tech-driven world.
Yeah, we're aiming for those aha moments,
Totally.
where you see how everything connects.
So we'll be navigating through an overview of electrical engineering,
The system of units.
which is super important.
Oh, crucial. The basics of circuit analysis.
And then we'll zoom in on the relationships between voltage, current, resistance,
And those laws that govern how circuits behave.
the governing laws, yeah. By the end, you'll see how these principles underpin everything.
From your smartphone.
To the power grid,
It's all connected.
it is all connected. Okay, so let's unpack this broad world of electrical engineering.
All right, let's do it.
At its core, it's a profession deeply rooted in applied science and math.
Mm.
And it really is the invisible force shaping so much of modern life, wouldn't you say?
Absolutely. It's
Yeah.
how we communicate, the computers we use, the control systems, power, signal processing.
It's pretty mind-blowing when you think about it.
It really is, yeah.
So for instance, think about the telephone.
Okay, yeah.
Electrical engineering is there from the moment your voice hits the microphone.
Through all those switching centers,
Routing your call, transmission over wires, or even as radio waves.
even pulses of light in fiber optic cables.
It's all circuits.
It really is, yeah.
And then there are computer systems.
Oh, yeah, huge.
From basic calculators
They're supercomputers.
to supercomputers.
Crunching massive amounts of data.
And those tiny integrated circuits?
Billions of components.
Billions.
Yeah.
It's incredible.
It's the edge of what's physically possible.
That's all thanks to electrical engineering.
And you have control systems.
Control systems, right?
Everywhere.
We encounter them constantly.
And often don't even realize it.
They regulate temperature in your home,
Manage your car's engine.
operate elevators,
Robotic arms in factories.
and even pilot airplanes.
It's amazing.
Power systems, of course, are totally fundamental.
Absolutely.
The way we generate electricity from nuclear reactions, water, fossil fuels.
And then distributed across vast distances.
Yeah, to power our homes and businesses, it's a massive feat of engineering.
And the reliability aspect is huge, too.
Oh, totally.
Like one failure shouldn't take out a whole city.
Exactly.
That takes some really clever design and backup systems.
All rooted in electrical engineering.
And then we have signal processing,
Signal processing, right?
where we take raw electrical signals and make them meaningful.
Like with weather satellites?
Capturing tons of data,
And processing it into those images we see on the news.
helping us understand and predict weather patterns.
Or even in medicine,
Oh yeah, good example.
CT scans. Using X-rays to create images of the human body.
Incredible technology.
And again, it's thanks to those signal processing techniques developed by, you guessed it, electrical engineers.
And it's really fascinating.
What's that?
How all these different areas, they're all interconnected.
Yeah, that's a great point.
Communication systems rely on computers. Control systems have computer hardware and software. Power systems need communication to manage the flow of electricity.
It's all woven together.
And signal processing is kind of used across all of them.
The textbook uses the example of a commercial airplane.
Oh yeah, a perfect example.
You've got communication between pilots and air traffic control.
Computer systems managing the engine, navigation,
Control systems for flight surfaces.
the plane's own power system.
And signal processing for noise reduction and interpreting sensor data.
It all comes together in this one complex system.
It really shows how interconnected everything is.
Right at the heart of it all is the electric circuit.
The electric circuit.
It's this mathematical model we use to approximate the behavior of a real electrical system.
So when we talk about circuits, we're talking about this model.
Yeah, not the physical hardware itself.
And for this deep dive, that's what we're focusing on, the model.
Now, it's important to understand that circuit theory is a simplified version of something bigger, something more complex.
More complex like what?
Electromagnetic field theory.
Okay.
But we can use this simplification because of three key assumptions.
3 key assumptions, okay? Let's break those down.
All right, the first one is that electrical effects happen instantaneously throughout a system.
Instantaneously. That sounds a little counterintuitive.
It does, but think about it. Electrical signals travel at the speed of light.
Or very close to it.
Exactly. So if the system is small enough, The signals move through it so fast.
And it seems like everything is affected at the same time.
Exactly.
So small enough is relative.
Yes, it relates to the signal's wavelength.
Uh,
If the wavelength is much larger than the system, we can treat it as lumped parameter.
Lumped parameter, got it.
And then this assumption holds true.
So like power systems at 60 hertz have a long wavelength
Hundreds of kilometers.
versus radio signals, much shorter wavelengths.
The textbook mentions a rule of thumb, the 1/10 rule.
The 1/10 rule, interesting.
Yeah, if the system size is less than 1/10 of the wavelength, circuit theory works well.
But for high-speed circuits, things can get tricky.
Yeah, the wavelengths get comparable to the component sizes, and then the assumption breaks down.
Okay, so assumption number 2,
The net charge on each component is always 0,
always 0,
so components might separate charges, like capacitors,
right?
but there's never an overall excess of one type of charge on any single component.
Okay, that makes sense.
And the third assumption is no magnetic coupling between components.
No magnetic coupling, okay.
It can happen within a component, like a transformer,
Sure.
but we assume no unintended magnetic interactions between separate components.
So these 3 assumptions make circuit theory possible.
Yeah. It lets us use simpler math instead of the complex math of electromagnetic theory.
And it's accurate enough for most engineering problems.
And sometimes engineers even design systems to keep these assumptions valid.
So they can use the simpler circuit theory tools.
Exactly.
Now, let's talk about problem solving in engineering.
Oh, a crucial skill.
It's not just knowing the theories.
No, it's about having a system to tackle those engineering challenges.
The textbook outlines some general steps.
Starting with identifying what you're given and what you need to find.
Know your goal.
Right, exactly. And sometimes you have extra information, or you need to make assumptions.
If some details are missing.
And it's always good to note those assumptions.
Just in case you need to revisit them later.
Exactly. The next step often involves making a visual representation.
Like a circuit diagram.
Yeah, a model. It just makes the problem clear.
You might need to add labels, values, to help with your analysis.
Then comes the critical thinking part.
Figuring out how to solve it.
Right. You have your toolbox of analysis techniques, but there's usually not just one way.
So you need to consider different methods, which one might be more efficient,
Exactly. And think about the potential problems with each approach.
and have a backup plan.
Always good to have a plan B.
Once you've chosen your method and equations, then it's time for calculations.
Put those math skills to work.
Accuracy is key here,
Absolutely.
but don't be afraid to use your creativity too.
Oh, for sure. If things aren't working out, step back, rethink your approach.
Maybe try a different method or even work backwards.
Sometimes you got to think outside the box.
And finally, you need to test your solution.
Does the answer make sense?
Are the units correct?
Is the magnitude reasonable?
Does it fit with your intuition about the circuit?
And it's good to check your work using a different method if you can.
And in real-world engineering, solutions are verified through multiple analyses.
Especially for critical designs, safety is paramount.
These problem-solving steps are guidelines, not rigid rules.
Adapt them to the problem at hand.
Develop a systematic approach that works for you.
Exactly.
Now let's switch gears and talk about the International System of Units,
Or SI units.
the common language of measurement in engineering.
It's how engineers around the world communicate.
Compare results, evaluate designs.
It's essential for clear communication.
The SI system is built on 7 base units.
Length, mass, time, electric current, temperature, amount of substance, luminous intensity.
The textbook probably lists them with their abbreviations.
And from these, we get derived units, combining the base units.
Like Hertz for frequency, Newton for force, Joule for energy,
Watt for power, Coulomb for electric charge,
and of course the volt for electric potential, ohm for resistance.
Siemens for conductance, and so on.
And to deal with very large or small values,
We use those standard prefixes.
like milli, micro, nano, kilo, mega, giga.
They represent powers of 10, making the numbers more manageable. Instead of saying 0.00001 seconds.
You'd say 10 microseconds.
Much easier.
Now that we've covered the basics of units, let's get into circuit analysis, the heart of the matter.
It's a crucial step in the engineering design process,
The textbook probably shows how it starts with identifying a need,
which leads to design specifications.
the criteria the solution needs to meet.
And then comes the fun part, translating the concept into a mathematical representation.
And that's where circuit models come in.
Right. They're built using ideal circuit components.
These are like the mathematical versions of real components.
Yeah, like batteries, resistors, but simplified.
But they have to accurately represent the real component's behavior.
Exactly. That's key.
And circuit analysis is where we apply math to these models to predict how the circuit will behave.
We compare those predictions to the design goals and make adjustments.
It's an iterative process.
You build a prototype, measure it, compare to the model, and refine.
And you keep going until the design works.
Circuit analysis is really fundamental to this whole process.
And since we're using models, it's important to use well-established ones.
Mature models.
Mature models, right.
They've been tested and used for a long time.
So we can be more confident in the results.
Exactly. That's the power of circuit theory.
We can represent real systems using these ideal components.
And describe their interactions with equations.
And those equations have to be in terms of measurable quantities.
Like voltage and current.
Which brings us to the definitions of those quantities.
The foundation of circuit analysis.
So it all starts with electric charge.
Right. It's the basis of all electrical phenomena.
It comes in two forms, positive and negative.
And in discrete amounts, multiples of the elementary charge of an electron.
And we see electrical effects when charges are separated.
Creating an electric force.
Or when charges flow.
That's our current.
So voltage is a measure of that electric potential difference.
The energy needed to separate those charges.
And current is the rate of flow of those charges.
Think of voltage as the pressure pushing the fluid of charge, current.
I like that analogy.
So voltage is energy per unit charge.
Denoted as V and measured in volts.
And current, denoted as I, is the rate of charge flow measured in amperes.
And because charge is bipolar, we need those references for polarity and direction.
Plus and minus, signs for voltage, arrows for current.
We'll see why those are important later on.
And even though current is the movement of individual electrons,
right,
we often treat it as a continuous variable.
Because there are just so many electrons.
Makes the math easier.
And that's one of the nice things about circuit models.
What do you mean?
We can analyze components based on their terminal behavior.
Yes.
The relationship between voltage and current at their terminals.
So even if components are physically different, if they have the same terminal behavior, we can treat them as identical.
Exactly.
But remember, circuit theory doesn't go deep into the internal mechanisms.
We're not looking at the detailed physics of how things work inside.
Just the observable behavior at the terminals.
Which brings us to the concept of the ideal basic circuit element.
The building blocks of our models.
So what makes them ideal and basic?
Okay, three things.
Three things, all right.
First, two terminals, the connection points.
Got it.
Second, their behaviors is described mathematically by the relationship between current and voltage.
Okay.
And third, they're indivisible, can't be broken down further.
They're the simplest units.
And ideal means they don't exist perfectly in the real world.
Right, they're theoretical.
But we use them to build models.
So we represent them as a box with two terminals.
With a voltage V and a current I.
And those references for polarity and direction.
Crucial.
So a positive V means a voltage drop from the positive terminal to the negative.
And a positive E means positive charge flows in the direction of the arrow.
And to keep things consistent, we use the passive sign convention.
Ah, yes, a very important convention.
It says that if the current enters the positive voltage terminal,
meaning it flows in the direction of the voltage drop,
then power P is P equal Vi.
and if it enters the negative terminal, P equals Vi.
It's all about being consistent.
It ensures our calculations are correct.
All right, last concept for this part.
Power and energy.
Why are they important in circuit analysis?
Well, because often the useful output of a circuit is non-electrical.
Like the motion of a motor.
Or the heat from a resistor.
Or light from a bulb.
And those are all measured in power or energy.
And we also need to consider the power limitations of real devices.
To make sure they don't get damaged.
So power is the rate of energy transfer.
Denoted as P and measured in watts.
1 watt is 1 joule per second.
And we have a relationship that links power, voltage, and current. P is Vi.
So power is just the product of voltage and current.
And the sign of power tells us whether energy is being delivered to or from an element.
And that's where the passive sign convention comes in again?
If we follow it, a positive P means the element is absorbing power.
And a negative P means it's supplying power.
Exactly.
So we've covered the scope of electrical engineering,
The importance of SI units,
the concept of circuit analysis,
and the definitions of voltage, current, power, and energy.
all with that crucial passive sign convention.
A lot of ground covered.
Okay, now for part 2, we're focusing on specific circuit elements.
Starting with voltage and current sources.
And then diving into resistance and Ohm's law.
Before we get into ideal sources, let's talk about electrical sources in general. They convert energy from non-electrical to electrical forms. or vice versa.
Like a battery.
Yeah, discharging converts chemical energy to electrical,
Charging does the reverse.
or a generator converting mechanical energy to electrical.
And a motor goes the other way.
Exactly. The point is, sources can deliver or absorb power.
And they're designed to maintain either a specific voltage or current.
Which brings us to ideal voltage and current sources.
Our simplified models.
So an ideal voltage source maintains a precise voltage across its terminals,
No matter the current,
and an ideal current source maintains a precise current.
regardless of the voltage.
But remember, these are idealizations.
They don't exist perfectly in reality,
Right. Real sources have internal resistance or impedance,
which affect their output.
and this leads to a restriction.
What do you mean?
Because the voltage is constant in an ideal voltage source, we can't describe its current just from its voltage.
Ah, I see.
And similarly, for an ideal current source, we can't determine its voltage just from its current.
We've traded some complexity for simplicity.
Exactly.
Okay, so we have two types of ideal sources.
Independent and dependent.
What's the difference?
An independent source sets its own voltage or current,
It doesn't depend on anything else in the circuit.
and a dependent source, or controlled source, does depend on another voltage or current in the circuit.
So its value is determined by something else.
Exactly.
In diagrams, independent sources are represented by circles,
With plus and minus signs for voltage, and arrow for current.
and dependent sources are represented by diamonds.
And we have 4 types of those.
4 types, okay.
Voltage-controlled voltage source, VCVS.
Output voltage is proportional to a controlling voltage.
Current-controlled voltage source, CCVS.
Output voltage is proportional to a controlling current.
Voltage-controlled current source, VCCS.
Output current is proportional to a controlling voltage.
And finally, current-controlled current source, CCCS.
Output current is proportional to a controlling current.
You need to specify the controlling variable, the equation, and the reference polarity or direction for each dependent source.
It can get a little complex.
It can, but it's manageable with practice.
So, sources are considered active circuit elements.
They generate energy.
And things like resistors are passive.
They can't generate energy, only store or dissipate it.
And the textbook might mention some rules for connecting sources.
Like, voltage sources in parallel must have the same voltage and polarity.
And current sources in series must have the same current and direction.
But you can connect a voltage source and a current source in parallel.
It all comes down to avoiding contradictions in the model.
Okay, let's move on to resistance and Ohm's law.
Resistance.
It's the property of materials to impede current flow.
We represent it with a resistor in our models.
Microscopically, it's the interaction between electrons and atoms in the material,
The electrons collide with atoms, transferring energy.
which turns into heat.
Sometimes this heat is unwanted, like in power lines.
But sometimes it's useful, like in heaters.
The amount of resistance depends on the material,
Conductors have low resistance.
like copper and aluminum, which we use for wires,
Insulators have high resistance.
like rubber and glass.
And Ohm's law gives us the relationship between voltage and current for a resistor.
It says that V equal IR,
If the current is in the direction of the voltage drop.
or V equal IR if it's in the direction of the voltage rise.
R is the resistance in ohms.
And we can rearrange it to get I equal VR, or I equal Nash VR,
Sometimes we use conductance, which is 1R,
measured in Siemens,
and in our models we use the ideal resistor.
where resistance is constant.
It's a simplification, but it works well in many cases.
Now, what about the power in a resistor?
Well, power is still P equal V.
But using Ohm's law, we can express it as PIWOR or P equal VRR,
And no matter the polarity or direction, power in a resistor is always positive.
meaning it always absorbs power, converting it to heat.
Resistors can't generate power.
So in part 2, we explored voltage and current sources.
Resistance and Ohm's law.
Now, on to part 3, where we tackle Kirchhoff's laws,
These are essential for analyzing more complex circuits.
where Ohm's law alone isn't enough.
Exactly. Ohm's law is for single elements, but Kirchhoff's laws are for interconnections.
They're based on conservation of charge and energy.
If we have a circuit like our flashlight with a voltage source and resistors,
We can't solve it with just Ohm's law.
we need more constraints from how the components are connected.
And that's where Kirchhoff's laws come in.
Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL.
Fundamental to circuit analysis.
KCL says that the sum of currents at any node is 0.
A node is where two or more elements meet.
And we need a sign convention Currents entering are positive, leaving are negative, or vice versa.
But the sum must always be zero.
Because charge can't just accumulate at a node.
And KVL is about voltages around a closed loop.
A path that starts and ends at the same node.
It says the sum of voltage drops, or rises, around a loop is zero.
Again, with a sign convention.
A voltage drop in the direction of travel is positive, a rise is negative, or vice versa.
This is because energy is conserved.
So we apply KCL to all nodes, KVL to all loops, and get a system of equations
Which we solve along with Ohm's law and other relationships.
to find all the unknown voltages and currents.
And in a circuit with n nodes, we get n1 independent equations from KCL.
The rest come from KVL and the element relationships.
And even with complex systems of equations, we can simplify things.
If we know the current through a resistor, we know the voltage.
And vice versa.
And if two elements are connected at a single node,
They're in series and carry the same current.
like in our flashlight circuit.
The textbook shows how to apply KCL and KVL to different circuits.
And a useful check is the power balance.
Total power generated must equal total power dissipated.
It confirms our solution is valid,
And finally, we have circuits with dependent sources.
where the source's output depends on something else in the circuit.
We still use KCL and KVL,
But we also include the dependent source's defining equation.
which relates its output to the controlling variable.
And that controlling variable is usually an unknown itself.
The textbook has examples of circuits with dependent sources
It's important to choose the right nodes and loops for our equations.
to get a solvable system.
And even with dependent sources, power balance still holds.
Always a good check.
So mastering Ohm's law and Kirchhoff's laws gives us the tools to analyze a wide range of circuits.
From simple to complex.
And that wraps up our deep dive.
We've covered a lot of ground.
From the scope of electrical engineering to the fundamental laws of circuits.
You've learned about circuit models, SI units, voltage, current, power, energy,
And the all-important passive sign convention.
and we've seen how to analyze circuits using Ohm's law and Kirchhoff's laws.
Hopefully this deep dive has clarified these concepts and sparked your curiosity.
We hope you feel more confident tackling those textbook chapters now.
Thank you for sharing your materials with us.
And for joining us on this first deep dive.
We encourage you to revisit those concepts with a fresh perspective.
And keep exploring the fascinating world of electrical engineering.
Until next time.